In this problem, we first have to write the Taylor series of this function g, which is defined as the primitive of another function, this function here, right? We have to write the series in powers of x. And finally, we have to determine what is the local behavior of the function near the point x equal to 0, whether this is a maximum, a minimum, or an inflection point, according to this expression, the Taylor series that we find. All right, first of all, we're going to write down the Taylor series in powers of x of this function here, f. Okay, and for that we need the Taylor series of e to the u, right, which is the sum from 0 to infinity of u to the n over n factorial. Okay, if we now substitute u by x squared, what we have is ex squared is equal to the sum from 0 to infinity of x to 2n over n factorial. And if we now make explicit the two first terms in this sum, n equal to 0 and n equal to 1, for n equal to 0 you have here 1 and you have here 1, so it is 1. And for n equal to 1, you have the denominator is 1, the numerator is x squared. So what you have is this. Okay, x to the 2n over n factorial. And this is very nice because what you have here is precisely this is the function that you're subtracting from this to get f. So f, the series, the power series of f, which is the difference between this and this, is just this series here. So it's the sum from 2 to infinity of x to the 2n over n factorial, right? Okay, so this is the integrand here, and now we have to calculate what is the series of this one given this series. So g of x will be equal to the sum from 2 to infinity 1 over n factorial, and then we have here the primitive from 0 to x of t to 2n dt, which is very easy to calculate. This is just t to 2n plus 1 over 2n plus 1, all right? And then you have to substitute this in 0 and x. And since this function at 0 is equal to 0, this is equal to x to 2n plus 1 over 2n plus 1. So g has the following power series. It's the sum from 2 to infinity of x to 2n plus 1 divided by n factorial to n plus 1, right? Okay, so if we explicitly write the first term of this series, first term corresponds to n equal to 2, so that is x to the 5, right, here, and then 2 here, and 2 times 2 is 4 plus 1 is 5, 2 times 5 is 10. So this is what this series or what this function looks like, very close to x equal to 0. This is true when x goes to 0. Okay, it's just the first term of this series, but that's enough information to decide what the behavior of this function, because this is telling us something. It's telling us that f0 and all the derivatives of f up to the fifth, so all these, right, are equal to 0, because there are no terms with a smaller power than x to the 5. And the first non-zero power is this one. Actually, 1 over 10 is equal to f5 of 0 divided by 5 factorial, which is 120. Okay, so if you multiply here 120, what you get is that f5 of 0 is equal to 12. In any case, it's 0 and a positive number. And that's all we need, because we have all the answers that we want. First, we know that the derivative is 0. So it is the point x equal to 0 is either an inflection point or a maximum or a minimum, so a local extremum. And that depends on what is the first non-zero derivative after this one that is that this function has. And the first non-zero derivative is this one, the fifth, which is odd. It's an odd derivative. So x equal to 0 is an inflection point. All right, inflection point. As a matter of fact, we don't even need to do this analysis, because what this expression is telling us is that locally, I mean very close to 0, this function is pretty much the same as this one. And if we plot this function, it is something qualitatively like this, right? So the derivative here is 0, but other than that, the function goes to plus infinity and to minus infinity in the two branches, and this is an odd function. This is x to the 5 over 10, right? And that clearly shows that x equal to 0 is an inflection point.